So today we will take up local histogram processing, and then we will go for solving some of the problems, and then we might take histogram development using statistics also. And further to that, we will do some spatial filtering techniques if time permits. Okay. So local histogram processing is the one wherein we define a neighborhood and move its center from pixel to pixel. So might be we will define what is known as 8 neighborhood, or what is known as the 24 neighborhood, that is 5 by 5. 8 neighborhood will just correspond to the 8 plus 1 9 pixels around it. You have a pixel, and around that you have 8 pixels. If it is 24 neighborhood, then it is 1 pixel there and 24 around it. That means it is 5 by 5. It's a 5 by 5. At each location, the histogram of the point in the neighborhood is computed. We just try to find the histogram of the points in the neighborhood. Then we can do the either histogram equalization or histogram specification or matching. Then we do the mapping of the intensity of the pixel centered in the neighborhood. Then next we move for the next location and repeat the procedure. So this is repeated for each pixel. Whatever steps are there here is repeated for each pixel. At each location, the histogram of the points in the neighborhood is computed. Either equalization or specification is done. Then mapping is to be done. Then move to the next pixel. So an example of this local histogram processing is given over here. So local histogram, so to say, equalization is applied. Result of the global histogram will be like this. So you can see that here you have the snow kind of thing in place of the white over here. But inside whatever is there here, you have a square here, a circle here, a triangular here, and might be something more here, and a here. Okay, all this is very lightly visible here, and here also it is very lightly visible. So global histogram is not solving the problem. So that's why we go for local histogram. If you apply local histogram, you can see that we have a square here. You have the lines here, you have a circle here, you have a single slant line and A over here. All these things are there inside, but not visible in either the original figure or global histogram equalization figure, but they'll be visible in the local histogram equalization being applied there. So for that, we try to write, the what you call formulas like this. M is equal to sigma Ri Pi, and URN will be equal to this. That is the what you call, nth, so to say, median. And this just gives you this is the what you call average, and this is the so to say expectation, and this is the nth median, and this is the what you call variance of the value. So and this is nothing but you have a formula here, 1 by mn double sigma x equal to 0 to m minus 1, y equal to 0 to n minus 1, and the value of the pixel itself, right? In this case, you have it as 1 by mn of double sigma f of x comma y minus the value m. M is calculated here. Now let us take an example for this. If you take an example over here, here we are given with a 5 by 5 matrix, right? It's a 5 by 5 matrix with values 0, 1, 2, 3, right? So this is 0 to 3 values. 0 to 3 means it's a 2-bit image, which is represented by a 5-bit matrix. Now, if you see here, how many times 1 is occurring, how many times 0 is occurring, how many times 2 is occurring, and how many times 3 is occurring can be found out. So if you see 0 is occurring 1, 2, 3, 4, 5, 6 times. So therefore, PR naught will be equal to 6 by 25. Totally 60, 25 pixels are there, out of which 6 are zeros. Therefore, PR naught will be equal to 6 by 25. That is 0.24. Then if you see ones, 1, 1, 1, 1, 1, 1, 1. So we have 7 ones. We have 7 ones in this figure of 25 pixels. So therefore, PR1 will be 7 by 25. That is equal to 0.25. Then 2. 2 is 1, 2, 3, 4, 5, 6, 7. 7 twos are there out of 25 pixels. So therefore, it will be 7 by 25. That will be 0.28. Then the number of threes, if you see 1, 2, 3, 4, 5, 5 of them are there. Therefore, PR3 will be 5 by 25 equal to 0.20. Now, if you substitute that in the formula for the what you call mean of the intensities, then we will get sigma I equal to 1 to 3 Ri PRi. Ri just means, 0 number of times, 0 is appearing, what you call 6 number of times out of 25, that is 0 into 0.24 is what we have written here. Ri value, if it is I is 1, then Ri also will be 1. 1 is occurring 7 times, so therefore 1 into 0.28 is what we are writing over here. Then when I equal to 2, R2 will be equal to 2. 2 is occurring, again 7 times, that is 2 into 0.28. That will be the value over here. Then 3 into 0.20, because 3 is occurring, 5 times out of 25, that is 0.20. Overall, we'll get the value as 1.44. This also can be found from directly the intensity of the pixel f of xy, denote the preceding 5 by 5 array, and using that we will get directly the value. So what it means is, you need to add up all the things over here, 0, 0, 1, 1, 2, 1, 2, 3, 0, 1, all these values you add and divide by 25. If you write again, you are going to get the value 1.44. Similarly, you can try to find the variance also. You can find the variance also. Okay, variance is not shown over here. That can be considered as a exercise. Okay, to find variance by both the methods. Okay, both the methods just mean that we are back to the what you call the formula over here and the formula over here. Use this formula and use this formula. You will get the value of the variance. Okay, so this is how we can find the variance. Resume the recording. So here it just shows a local average intensity and local variance by defining the neighborhood SXY. So in the neighborhood, if you say, then say if you have an image which is 256 by 256, the neighborhood can be defined for only 5 by 5. So for each neighborhood, you can take the what you call values and try to find out. So now you can see that we have here the what you call original image of a tungsten filament, which is so to say what you call we have a bar over here to which this tungsten wire is wound. Okay, we are winding the tungsten wire around a bar. The bar might be an insulator. Okay, tungsten wire will be the conductor which is wound around a insulator. So then this might be something like 130 into 130 pixels image, and the result of the global histogram equalization is shown over here. Now you can see that we have improved this signal to this extent over here, but whatever the blackened portions are there, they have not improved much. Whatever we have here, we have not improved them much. Only a little improvement is there over here. The contrast portion over here. Whereas a local histogram, if you see over here, is what you call whatever we have here, almost similar to that we have here. A little improvement might be there, but the the dark portions are improved much more. The contrast for that is increased much more. So the image enhanced using the local histogram statistics is shown over here, for which the formulas are considered like this. Okay, local histogram formulas where SXY is the local area which we consider, as I said, it might be 5 by 5 out of either 130 by 130 or 256 by 256. So only in that area we take the expectation. In the other area, we just leave it as it is. That is what we have. So like that, we can keep on repeating for the whole of the points, all the points in the what you call image. So if we try to do that, then we are going to get this type of figure. If you take the total local histogram statistics, we are going to get this figure. You can see that this is a much enhanced image using the local histogram statistics. Okay. Then we come to the spatial filtering. A spatial filter consists of a neighborhood and a predefined operation. We consider a neighborhood and then a predefined operation. The predefined operation might be convolution, correlation, averaging, or anything of that sort. So linear spatial filtering of an image of size m by n with a filter of size small m by n is given by the expression. Okay, so we have here an image of size capital M by n, and we take a filter of size only small m by n. That is, again, we are talking about the neighborhood of m by n. Then at that time we can write the expression something like this, and this is nothing but the correlation function. Okay, the correlation function. An example of this can be considered like this. So this is f of xy. Around it you have the 8th neighborhood where we can write f of x minus 1, y minus 1 on this side, and f of x plus 1 and y plus x plus 1 on this side. Now for this neighborhood, okay, for this neighborhood you can take the weights also correspondingly as w of minus 1 till w of 1 comma 1. Then you multiply the corresponding quantities over here, corresponding to this over here, corresponding quantities over here, and then get the final result. And put it over here. Put it over here. That means consider these points and then give a weightage for that, multiply and find the correlation and substitute in place of the corresponding pixel. So the correlation of a filter WXY of size m with an image f of xy is denoted by WXY, a star without, what you call opaque star over here, f of x comma y. Okay, this is the formula. Now, similarly, the convolution is specified by a star which is darkened, and that's what we write over here. So only difference between this and that is here in the correlation we have plus signs. Here in the convolution we have minus signs. Okay, minus signs. That's the only difference. So let us take some examples corresponding to this. Illustration of 1D correlation. Whatever we have shown in the figure is 2D, but now we are taking here 1D correlation and convolution of a kernel W with a function f consisting of discrete unit impulse. Okay, discrete unit impulse. So function f is discrete unit function f is discrete unit impulse. Note that the correlation and convolution are functions of variable x, which acts to displace one function with another. For the extended correlation and convolution results, the starting configuration places the rightmost element of the kernel to be coincident with the version of F. Additional padding must be used for the same. So this figure is a little hazy, so we'll take this figure over here. So this is correlation and this is convolution. The original value of F is written over here with the original virgin over here. You can see that this is an impulse because 1 is present only at one place, whereas W is this 1, 2, 4 to 8. So starting point alignment, we'll try to do 4 over here. 4 is at this point. Okay. So 1, 2, 4 to 8 is what we write. And then we do the zero padding at these points. So we might be bothered about the point which is 4 over here. Right. So zero padding will do. And then you can calculate the value for this. That means multiply 1 with 0, 2 with 0, 4 with 0, 2 with 0, 8 with 0, and then all these are considered zeros only, 0 with all these, and add. If you do that, you are going to get a value 0. If you multiply this with this, 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 and then 0 with this, and 0 with this, and all that, and then add, you will get a value 0. Then the starting, what you call, whatever is there over here is moved 1 bit to the right. So if you move 1 bit to the right, then you will get this one under this 0. This 2 will be shifted 1 bit. 8 will go below 1. That is what we are having over here. So now again corresponding bits multiplication, 0 into 1, 0 into 2, 0 into 4, 0 into 2, 1 into 8, and then we'll get 0, 0, 0, 0, 0, 8, and add all of those terms, 0 plus 0 plus 0 plus 0 plus 8, you'll get the value 8, and that is what is written over here. Then once more you shift that, then you'll get under 1 the value 2. So if you multiply and add all of them, then you'll get 2, and that's what is written over here. If you shift 3 bits position there, after 3 shifts, okay, this is 1 shift, this is 3 shifts over here. After 3 shifts, if you do, then 4 will come exactly below 1. So again, if you multiply each one of them and then add, you'll get 4. Like that, you can keep on repeating till the fag end, right? So therefore, we'll get the value which is like this. And then if you extend it by the full result, you are going to get this. Convolution will be just, rotate W by 180 degrees and repeat the same process. Convolution will be rotating W by 180 degrees. First becomes last, last becomes first. That is what is 180 degrees shift. Okay, 8 to 4 to 1 is what we will get here in that order. That is 180 degrees rotated. So after doing 180 degrees rotation, then repeat the same process whatever we have done over here, and we are going to get this convolution result like this, and the extended convolution result will be in this format. Now this can be repeated for a two-dimensional quantity also. Like this, we have here the F, a two-dimensional value, and W, the weights being mentioned over there, and then you'll get the convolution of that with respect to only one bit. You'll get the initial position. We are just padding it over here. We are just trying to add padding positions to this padded F, and then we fix the initial position of the W, and then we get the full correlation result by taking this with the correlation of this with this, and that will turn out to be this. Then the cropped correlation result will be like this. Cropped just means we remove the whatever is padded values, so they will get it like this. Then for the case of the so to say convolution, then we rotate the value of W. The W is like this, and we rotate it and put it like this by whatever 180 degrees in both the directions. That is, you have the so to say the rows and columns all are exchanged over here, so that we'll get this value, rotated value. And then if you take the what you call convolution of that with the value of f, we are going to get the full convolution result like this, and the cropped convolution result like this. Okay. So if you see these two over here, either you can see these two, or you can see this with this. So you can see that in place of 1 being here, 1 is coming here. In place of 9 being here, 9 is coming over here. And 3 and 7 are also exchanged. Like that, you have 6, 8 here and 6, 8 coming at this place. 2, 4 here and 4, 2 coming at this place. That is the rotated one. So thus we can get the correlation and the convolution for both of them together.